Okay, I don't know. Maybe we can start. If you're ready.
Sure. Okay.
So, yeah, good morning or good evening, good afternoon to everyone, depending on where you are. So, it's my pleasure to introduce our today's speaker, Dr. Sinha, who is an electrical engineer in Pacific Northwest National Laboratory. His research interests span operator methods for dynamical systems, causal analysis, and geometric control. Dr. Sinha completed his bachelor's in electrical engineering from Yadapur University, India, and master's in systems and control from Indian Institute of Technology, Bombay. He was a PhD graduate at Iowa State University, where he developed the notion of information transfer to characterize causal structure in dynamical systems. So Dr. Sinha will talk about Koopman operators and symmetry. So yeah, the floor is yours.
Yeah, thanks, Eric. So, hi everyone. So today I'll be talking about Koopman operators and how they interact with equivariant dynamical systems. So by equivariant, I mean symmetric dynamical system. So this work, well, it originated from while we were working. So this work, the first work that I'm presenting, so I'll be presenting two works which are related. The first work, this was done with two of my colleagues. One is Sai Pushpak and the other guy is Enoch Young. So at that time he was at PNNL, and now he is a faculty at UCSB. So there we were in that paper. What we are trying to do is we were trying to look at we are trying to compute a global Koopman operator by computing local Koopman operators, and we are trying to fuse them to get the global Koopman. And there we had an example of this bistable toggle switch, and and this is how the equations look. And you can see that this system is symmetric under the transformation x1 goes to x2 and x2 goes to x1. And then in that work, what we are trying to do is we computed local, and now in this system, you can see from this phase portrait, it has two invariant sets. And what we did was we computed local Koopman operator in this invariant set and this invariant set. And then we tried to fuse, and we were looking at how to fuse them. But while we were working on this, what we noticed is when we are computing these DMD matrices in these two invariant regions, we found that these two DMD matrices, the entries, if you look at the entries are the same in both of them, only they are rearranged. So that basically, we started to think that, okay, is this some coincidence or is the symmetry, underlying symmetry playing some role? And what we noticed is these two matrices are related by a similarity transformation. So that was the motivation for this work. And then we realized that, okay, this may not be, we checked this same thing with the Lorentz attractor as well. And we found that, okay, there also this intuition holds true, and that gave us the confidence to look into the theory of what is happening here. So now the question comes, why do we need to talk about symmetry at all? So symmetry is one of the very basic concepts and very fundamental concept in physics and in many physical objects. And even the most of the laws of nature, they have some inherent symmetry in it. And again, you have one of the most important theorems in all of physics is Noether's theorem, which is used in both classical and quantum mechanics. And another related concept, which is extremely important, which is related to symmetry, is symmetry breaking. So yes, symmetry, it's nice, it's beautiful, but interesting things happen when this symmetry is broken. So in this work, we will discuss how Koopman operator interact with symmetric system, and then we will provide entropy-based measure to predict this symmetry breaking in dynamical systems. So now let's look at what we mean by a symmetric or equivariant dynamical system. So for now, one can do this for both continuous and discrete time systems, but the intuition is easier to understand in discrete time. So I will be discussing it in discrete time for discrete time systems. So we consider a discrete time system from Rn to Rn, and the dynamical map is given by T. Then now let's say a group G acts on X. On X, I mean the state space, and there is a map phi from G cross X to X. Now this system is said to be equivariant if this diagram commutes. So that means you first map you take a point X on the state space, you map it by G, then you transform it by T. This should be the same as first you evolve X by T and then you act by the group. If this equation holds true, then the system is said to be equivariant. And for continuous time system, it's a map from the tangent space. So you have to look at the tangent space because the vector field, they belong to the tangent space. So now once we have this abstract group acting on the state space, since we assume that this system is embedded in Rn, one can look at the representation of the group. So what do you mean by representation? Yes, representation has a proper meaning in mathematics, and for any group G, linear representation of a group is basically a homomorphism from the group to GLV, where V is a vector space and GLV is the general linear group on the vector space V. So now given any element G in the group, and once we have a representation, that action of the group element G can be represented by a matrix gamma G. Once you fix a basis and all those things are there, but the main point is the action of this abstract group on a vector space can be represented by a matrix, and this is known as the representation theory basically studies the properties of the matrix, the invariant spaces, and all those things. So in this work we will basically, since we have to work with data and stuff, we have to look at this representation. So that's why we define this representation of a group. So with this, now let's look at this, how this Koopman, let's investigate how Koopman operator interacts with the symmetric systems. So before we begin, let's define this notion of an isotropy set. So isotropy set for a trajectory or for a point is basically all those elements of G or the group which fixes the trajectory or fixes the state. So you can either you can talk about the isotropy set of a point or a trajectory or even of a set. It doesn't matter. So now with this, one can show that this isotropy set, it forms a subgroup of the symmetry group G. So that is quite is straightforward to prove, and I can also prove that if these are the two. So let's say we take trajectory x0t, and then we take a group element G, and then take the or the isotropy set or the isotropy group of this trajectory, of the entire trajectory that is mapped by the group element. Then one can show that these isotropy groups are related by a conjugation of by this group element. So this is one of the important results which will uh, come up later, and from here probably you can guess that okay, why this similarity transformation comes in. So once you have this action, basically this conjugation relation holds true throughout. So this kind of gives an intuition that okay, these Koopman operators may be related by a similarity transform. So I think you guys all know this. So this is like, okay, what do we mean by Koopman? So I don't want to go over this because this, or okay, I guess every one of you knows this. So now what do we have? We have an action of a group on the state space. But our goal is to see how the Koopman operator interacts with this group action. So to do that, we have to extend this group action from the state space to the space of functions. And the way to do it, first we define a map phi from G cross G times Fm to Fm, but where we define the action of the group element G on any function f belonging to Fm as this thing, if G star f of x goes to f of G inverse x. And with this, one can show that this map phi defines a group action on the state space. And another, and what follows from this from this is the following, that consider the set sigma f. So sigma f is again the set of all group elements which fixes these functions. So if you consider this set, then you can show that for a function f, this isotropy set or the set which fixes f forms a normal subgroup of the group of the symmetry group G. So now we have the following result. This is the one of the main results of this work, that okay, if you be a Koopman operator of the system of a G equivariant system T xt plus 1 equal T of xt, then one can show that this group element basically commutes with the Koopman operator. So G composed with U is same as U composed with G. So this is where this similarity transformation comes in. And then once you go into this finite dimensional approximation, then this action of G is exactly the is replaced by the n-dimensional representation matrix of the group element, or of the group. So now we have this, but here we are fixing F. Now let's say let's consider U, which is let's say okay, let me be clear. So let's say we have a function F, and let U be the UF be the representation of the Koopman operator with respect to F. So abstractly, you can think of this as, okay, we have a linear transformation. Abstractly, that linear transformation is fixed, but once you change the basis, that representation changes. So here we are using that same idea that, okay, you have a system, you have a Koopman operator, but depending on which function you choose, that representation changes. So now if you take two sets of function, one F and another one F hat, where F hat is basically G acting on F, and let UF hat be the representation of U with respect to F hat, then one can show that this is how these two these two representations are related. So one can prove that. So why I'm talking about this? Because this will come up in the come up later in the finite dimensional approximation case where we do it from data. So one can also, okay, now we look at how the group action interacts with the eigenspace of the Koopman operator. And then, in fact, it is kind of easy to show. In fact, these results are kind of straightforward, and it just follows the intuition. And one can show that under this group action, these eigenspaces also remain invariant. And now we look at how, so now let's say we have this system, a stable system on a compact manifold, or a compact subset of Rn. And then let's say we have this decomposition of the state space into invariant sets. So then one can show that if Mi is an invariant set, and then if you consider the set G times G acting on Mi, that is the set of all x tilde belonging to M, such that x tilde is G of x, one can show that G of M is also an invariant set. And then in fact, this kind of makes sense. So in fact, what happens is basically the group kind of acts transitively on the system itself. And so we use this to come up with these relations in the finite dimensional approximation case as well. So what is our goal? So let's say our state space can be expressed as a union of invariant sets, and where Mi intersect Mj is empty. And let's say on each of these Mi, we fix a dictionary, psi I. And then our goal is, and then let's assume that this group acts on the system transitively, that is, there exists some G such that G times Mi belongs to Mj for I not equal to J. So our goal is to see whether there is any relation between Ui and Uj. So now this can be done in two ways, right? One is we have the same dictionary function on both Mi and Mj, or we can take psi I and G times G acting on psi I as the dictionary functions on Mj. So in these two cases, we have two different results. So one is if we use the same dictionary function on both Mi and Mj, then the local Koopman operators, they follow this relation. And this is exactly that similarity transformation relation that we observed in the first slide. So that kind of clarifies, okay, why that coincidence was happening basically. And the second result is if we use psi I and G star psi I as the two sets of dictionary function, then you get them as to be equal. So now with this, we will again come back to this equation, the bistable toggle switch, which we already saw, and we can verify that these two are related. These two local Koopman operators are related by this similarity transformation. Similarly, for the Lorentz attractor. So Lorentz attractor again is a symmetric system with the symmetry group isomorphic to Z2. And the three-dimensional representation of the non-trivial element is this matrix, diagonal of -1, 1, -1, -1, and 1. And then you can also see that if you compute the local Koopman operators on this space and this space, then again they are related. And the third example where we looked at is this Hamiltonian system, where the Hamiltonian is given by this, and it has four invariant sets, and one can compute that the symmetry group for this system is the Klein 4 group. It's Z2 cross Z2, and with the present, and this group can be presented in this way. And the symmetry operations and these equations remain symmetric under these operations. So qp goes to pq, qp goes to minus q minus p, and qp goes to minus p minus q. So these are all the symmetry operations that the system respect. And with this, if you find all these local Koopman operators, you can verify that all these similarity transformation relations are being respected when we compute it from data. So now that we have seen how Koopman operator interacts with a symmetric system, now let's talk about symmetry breaking. So what do you mean by symmetry breaking? Now let's say we consider a equivariant parametric system which is parameterized by mu, such that a pitchfork bifurcation occurs at mu equals mu c. Now, for the intuition for intuitive clarification, let's think about a system which is governed by a double symmetric double well potential, so that the equation of motion is given by this. So now for a less than 0, this system has only one stable equilibrium at the origin. But for positive a, this stable equilibrium at the origin, it splits into two stable equilibrium, and the stable equilibrium at origin, it becomes unstable. So now if you think about the trajectories of the system before the bifurcation, what happens is the trajectories, they settle to the origin, and all the solution they respect they respect all the solutions, they respect the z2 symmetry of the equations. Okay, but what happens is when that system splits into when that equilibrium, that stable equilibrium becomes unstable and it splits into two stable equilibrium. Now a trajectory, it settles into either one of the equilibriums, right? And then what happens is the isotropy or the symmetry group of that particular solution is not the entire group, because the trajectory spontaneously chooses one of the wells, right? So this is known as spontaneous symmetry breaking. And here we analyze basically this phenomena of spontaneous symmetry breaking. So the definition of classical spontaneous symmetry breaking is the following. So let's say you have a system x dot equals f of x mu, be a symmetric dynamical system with attractor m mu. Now suppose that for mu less than mu c, the attractor m mu has an isotropic group G. After bifurcation, we say that spontaneous symmetry breaking has happened if for mu in this, when mu is greater than mu c, this attractor m mu has a isotropic group which is a proper subgroup of the original symmetry group. So this is how symmetry breaking, local symmetry breaking is defined, and this is this is a very standard result in literature, where you can show that as the system is approaching this symmetry breaking or this pitchfork bifurcation, the trajectories, they basically slow down, and this is known as critical slowing down. And one can show that this critical slowing down is accompanied by a growth in the covariance as the system approaches this instability. So now, since this covariance increases, so the idea was, okay, if the covariance increases, that means the entropy of the trajectory system should also increase as it approaches instability. And in fact, this is what one can show, that okay, there is one assumption that we consider the linearized system instead of the nonlinear one, because we are looking at this parametric form, and we are looking at as the system is evolving, but we are looking at the steady state. We're not talking about transients. For each fixed mu, we look at the steady state solution, and for that we can basically talk about the linearized version of the system. Of course, we assume that it's well behaved and stuff, but under those assumptions, one can show that as the system is approaching this instability, its Shannon entropy basically diverges. Now, this entropy diverges. Now, our idea was, okay, since the entropy of the system is diverging, the entropy flow between the states should also start to increase. And this is, in fact, what is known as information transfer. So this is in continuous time. So how do we define information flow? So let's say we have a two-dimensional system with states x and y. So what information transfer does is it quantifies the amount of information that flows from any state, from a state x to the state y, to state y, as the system is evolving. In discrete time system, it's easier to understand what's going on. So what it does is, so let's say the system, you have a discrete time system and it is evolving, and let's say you have two states x and y. So the information flow from state x to state y as the system is evolving from time step t to time step t plus 1 is the following. you consider the total entropy of the state y at time t plus 1. The total entropy of y at time t plus 1 is the total entropy of y when x is not present in the system plus the entropy of y when plus the entropy that is being transferred from x to y. So this is the intuition of the definition of the concept of information flow. So the information flow is defined as basically you have the total entropy of y equals to the sum of entropy of y when x is not there in the system plus the amount of entropy that is being transferred from x to y. So in other words, you can say that the amount of information transferred from x to y is the total entropy of y minus the entropy of y when x is not there in the system. And this notation, this x not of x, this notation is exactly saying that this says that this is the entropy of y when x is not there in the system. So with this, one can show that the steady state information transfer is basically this is given by this form where we are partitioning the linearized version of the system into this form, into this block matrix form where axis is the interaction of the x term with itself, axy is the influence of y on x, and similarly ayx is the influence characterizes the influence of x on y, and ayy is the self-interacting block of y. And with this, one can show that as the system is approaching this instability, this provided that this ayx is non-zero, the information flow from x to y that shoots up. One can show that. And with this one, so let's go consider this two-dimensional system. Again, it's just a pitchfork bifurcation here. So for mu less than 0, we have one stable equilibrium, and as mu becomes positive, if this single stable equilibrium splits into two unstable equilibrium, into two stable equilibrium, and the equilibrium at origin becomes unstable. And now we see as we increase the mu, as we approach mu equals 0 from below, the entropy flow from x to y starts increasing. And in fact, if you see that the information flow from x to y increases, but the information flow from y to x doesn't increase that much. So why is this? This is because unlike mutual information, unlike mutual information, this information transfer metric, it is asymmetric in x and y. And that is why it can capture the causal direction. So what I'm saying is, you know that correlation doesn't imply causation. So this information flow, what it does is it basically sees, okay, x is influencing y and y is not influencing x. So it kind of quantifies that. So again, this idea originated because we were trying to do the causal, we're trying to identify causal structure of dynamical systems, and what we found is the concepts of directional information flow or transfer entropy, those quantities, they cannot capture the true causal structure in a dynamical system. Forget nonlinear system. Even for we have shown that even for very small three-dimensional linear system, transfer entropy does, or Markos directional information flow, they do not, or even masses bidirectional information, they do not capture the true causal structure. It captures some kind of statistical dependence. So basically what it is doing, what we realized is those measures, they don't take into account the time evolution, the temporal dependence. And that's where we came up with this notion of information flow. And we showed that, okay, it is asymmetric in x and y, and it captures this directional information flow. And okay, so here we see that this in this symmetry breaking case, this information flow increases. The information flow increases as the system is approaching this pitchfork bifurcation. But you may have noticed that in this, while we are detecting this approach towards instability, though we started with symmetry breaking, it has nothing to do with symmetry breaking per se. It's more to do with the system approaching instability. In fact, and we have used this to use this notion to analyze other systems as well. So these are some other application of this information transfer framework. So let's talk about the power system first, because this is more related to the stability thing that I talked about. So here, if you what we did is we tried to characterize the causal structure and also characterize the stability in a power system. So what do we mean by characterizing stability? So in power system, what happens is they have different notions of stable instability. So you can have voltage instability or you can have angle instability. And in power networks, power systems literature, it is not, there are no methods that says or that can classify or that can infer whether one instability is voltage induced or is it angle induced. There are only a few, one or two very uh, prototypical IEEE systems where this has been done. One of them is the three bus system. So it's a very small system, and there what happens is as the load is increased, first there is a Hoff bifurcation at S2 and there is another saddle node bifurcation at S3. So at S2 what happens is here the system becomes unstable, and it is known in literature that at S2 it is the voltage, it is the angle variable that causes the instability. So this is at S2 it is angle instability, whereas it is known that at it's at S1, at S1 it is angle instability, and then at S3 it is a, here it is a voltage instability. And then what we found is if we compute this information flow between the between the states of the generator, we find that near S1 the information flow from the angle variable shows this sharp increase, whereas near S3 it is the information flow from the voltage variable that shows this increase. So this information flow, it not only identifies that the system is approaching instability, it also identifies which variable is responsible for that instability. So it identifies the cause of instability as well. Another application that we found, what we had, is basically identifying the network topology from time series data. So we compared it with standard methods like with transfer entropy or with Nathan Cood's Cindy, and we found that this IT framework works much better. And another application that we worked recently is on identification of causal structure in atmospheric systems. So what we did was we were trying to identify the chemical species that facilitate. We shouldn't use the word facilitate. So with that. One should say the chemical species which are responsible for production of organic aerosols in the atmosphere. So organic aerosols are not a desirable chemical in the atmosphere. So it leads to climate change and global warming. So that's why it is necessary to identify which chemicals are responsible for formation of organic aerosols. And there we looked at the chemical kinetics. We had those differential equations, and then we had the dynamical system. From there, we had the data, and we computed this information flow. And this is the causal structure that we identified, which really which matches with the chemistry of the system. So these are some of the applications that this information flow has. And yeah, so thank you. So yeah.
Thank you.
Yeah. Oh, enough. Yeah.
Now
That's
we have
pretty.
time for questions. I think you know.
Yeah, this was quite fast. Yeah, I didn't want to go into. Okay, is this a way to distinguish a first order connect? Yes, 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 yes. In fact, in continuous time setting, it is a bit. I don't know how exactly to do it, but in discrete time setting, this is one of the biggest advantages of this information flow. So so for others, if you so what Enoch is asking is, so let's say you have a three-state system. Now A is influencing B and then B is influencing C, but there is no direct influence from A to C. So basically A is influencing C via B. Now can we distinguish between direct influence and indirect influence? In fact, our information flow for discrete time system, it can do that. So while I was explaining this intuition of information flow, I said that okay, information transfer, what it does is it computes or it quantifies the amount of entropy that flows from state X to state Y as the system evolves from time step t to time step t+1. So this is what known as, we define this as one step information flow. Now you can do the same thing. You can play the same game. And instead of looking at the evolution of the system from time step t to t+1, you can look at the evolution of the system from time step t to t+2 or t to t plus any k. So if you look at that, that will give you k-step information flow. So now coming back to this question, so now let's say we have a system where A is influencing B and B is influencing C, whereas A is not influencing C directly. In that case, what you will find is you will find the one-step information flow from A to C to be zero, whereas this two-step information flow from A to C will be non-zero. In fact, we have shown this in one of our previous papers that and this is one of the big advantages of this information flow, whereas Granger causality or transfer entropy, they cannot distinguish between direct and indirect influence, whereas our notion of information flow can do that. Yeah.
Fantastic. That's really beautiful work, Subhrajit. And as you know, I'm thinking a lot about this right now these days. I'm
Oh,
working on a paper, so I'm happy to chat with you more.
sure, sure. We can talk. Yeah, we
I,
can talk.
one question I have then to follow up is just how does this contrast or contextualize with the work of Eduardo Sontag and his collaborators when they were doing cancer research? They determined that to discover network structure,
Mhm.
that you would have to do targeted perturbations at each individual node.
I
Um,
I think
do
this
you
is
have to do targeted perturbations with your technique at each
no,
node?
no, I don't need to do that, because once you do it, when you are doing it from data, I'll explain it for 2D system. It's easier for 2D system, and we are doing DMD everywhere. Okay. So let's say you have a data x, let's say x0, x and y are your two states. Now you have data, let's say x1, y1, x2, y2 in this way. So now you do DMD on that. You compute the linearized version for the entire system. Now the trick is, now the difficult or the non-trivial part is how to compute this freezing dynamics, because what is this information flow? Entropy from x to y. It is entropy of y minus entropy of y when x is not there in the system, in the sense that we are not evolving x. We are in the second case, we are basically fixing, we are treating x as a parameter. So we forcefully freeze x. So now that once we have this data, that x1 y1 x2 y2, now we basically what we do is we create a synthetic data set, and that data set looks as x1 y1 maps to x1 y2. So that's where that x variable is getting frozen. So now this data set is x1 y1 x1 y2, then x2 y2 x2 y3. And now once you do DMD on this data set, you get the frozen dynamics, and then you can do the do if basically you have the formula for information flow, you use that. So this is where this targeted, what you are saying, the targeted perturbation, this is what how we are doing it. We are freezing this X dynamics. In fact, this is very similar to Julia-Pearl's do calculus, where you freeze one of the variables, or you part of one of the variables. This is very similar to that. Yeah.
So fantastic. That's really helpful. So that is a form of this freezing is kind of like it's like a form of a perturbation in my head. I may be
Yes.
thinking about the wrong way, but it's sort of like a perturbation. So it satisfies the informativity conditions that Sontag said were essential to any network identification problem. And is there a relaxation for when you're dealing with a network and you're observing it post hoc and you cannot necessarily freeze a specific node in the network? Is there some sort of relaxation of the technique?
See, when you cannot so let's say you are doing an experiment where you cannot freeze one of the variables. So this is where this data thing comes in, that I explained. That okay, you have the data now. You basically construct another data set. You already have the state data. You compute the DMD matrix from there. That's the DMD matrix for the original system. Now for the frozen system, or this part of, it's not exactly the intuition, you can think of it as perturbation. It's like you can think it as a complementary thing. Right? Okay, I want to, so perturbation means what? Let's say I want to see how X is affecting Y. So here by perturbation, what I do is I perturb X. But in the information flow, what we are doing is we are freezing X. So we are basically saying that, okay, I don't want to see the effect of X. I only want to see how Y is evolving on its own. Look at the entropy. Then look at the entropy when the entire system is evolving, and you just subtract one entropy from the other. So this is like, you can think that this is like a dual way of dual two perturbation. In perturbation, when you basically perturb X, but in IT you freeze X. And once you freeze X, so the thing is, okay, now this your question comes in, that if we are doing an experiment where you cannot perturb X, so then this perturbation technique won't work. But now when you're doing this information flow, once you have the data, you can create this synthetic data that, okay, X1, Y1 is mapping to X2, Y2 in the original system. But in the frozen system, what is happening is X1, Y1 is being mapped to X1, Y2. So that is done by the operator himself. This is a synthetic data set that is being constructed from the original obtained data set. And this synthetic data set, what it mimics is it is basically mimicking that frozen dynamical system where X is held frozen. So once you do the DMD on this frozen data set, you basically learn the system where X has been held frozen. And now you can compute the entropy of each of this system, and then you just subtract them.
But wouldn't this then, I guess then aren't you making in so doing, then are you sort of saying, suppose that the network topology as represented by the current simulation, the synthetic data set of your system is a certain way, how well does that match up to what we see in experiments? I guess that's something maybe I can take with you offline. It's like a detailed
Yeah.
question.
Sure,
I'll have to
sure.
read your papers and then I'll follow up
Okay,
with you.
okay.
That's a very neat
Sure,
idea. I really like it. Very clever.
Okay, I can send you 1 or 2 papers where maybe the power system one, that would be nice for you to see. Power system and also the network topology identification paper. I can send you those 2.
Sounds great. Sounds great. Thank you so much,
Yeah,
Subhrajit. Thank you, Irvin, for the floor. Appreciate it.
thanks. Yeah.
Do we have other questions maybe? Okay. Thank you very much for your talk.
Thanks.
Yeah.
Okay.
See you all.
See you.
Bye-bye.
Bye.